excuse me. Hello everyone. I will go ahead and help you with chapter 23 homework. Which of the following elements has the ground state electron configuration? So we are given a configuration and we need to find out what is the element. So how can we do this one? We are given, look at the given electron configuration, and we are given xenon as your noble gas prior to the element. And you look up your periodic table, have a periodic table in front of you, and xenon, if you look at, which is a noble gas, and it has 54 electrons, right? So with xenon 54, and then you have in the 4f sublevel there are 14 electrons, 4f14, so you add 14 to that. And in the d level you have 10. In the fifth level of the d electron there are 10, d10, and there is 1 s plus 1. So you add up all these. You had 54 plus 14, 68 plus 10 plus 1, that will give you 79. And then you refer to the periodic table and see which one is 79 atomic number. Okay, so that's going to be gold. Okay, and find out what is a symbol for gold. That's how you calculate. If you are given the configuration, how you find out the element. Okay, number 2. Which one of the following has the ground state electron configuration, which is this one? Again, we have argon, and you look up your periodic table. Argon element has 18 electrons. And then 3d10, meaning there are 10 electrons in the 3d level and 1 electron in the s1. And then you add up all these things and find out which one is the element 29. Okay, so you can find out the correct answer. That's how you do number 2. And then the third one, the most common oxidation state for ions in the transition elements. We talk about this in the lecture. In the transition elements, they have s2 electrons and then the d electrons. So it's always s electrons that's going to be lost. So because of that, plus 2 is the most common oxidation state. For inner transition elements, that's going to be plus 3. But for the transition elements, plus 2. Okay. And then the fourth one, the ground state electron configuration, chromium plus 2. First, we need to find out what is the atomic number for chromium. Chromium is 24. And before you go for chromium 2 plus, first you have to write down the electron configuration for chromium. Again, refer to the periodic table and locate chromium. So chromium is in the 4th period. And prior to chromium, we have argon as the noble gas. And then after argon, you have to go to the 4th period. First electrons that's going to be filled is the s orbitals. That's going to be your 4s2. And then after calcium, which is the 4s2, you have to go until you meet chromium by filling d electrons. So the chromium is the 4th element in the d block. That gives chromium 3d4. Remember, always the d sublevel going to be n minus 1. N is the principal quantum number, which is 4. So 4 minus 1 is 3 for d, 3d4. But we learn that when you have 4s2 d4, it would be more stable when you have 4s1 3d5. That's going to be the electron configuration for chromium. What about chromium? This is for chromium that I have written. But for the chromium plus 2, meaning it's going to lose 2 electrons. So it's going to lose 1 from this one of the s electrons, s1, and then another one from the 5. So when you lose one from here to make chromium plus 2, That's going to be then argon. Nothing in the 4s level, and it would be 3d4. Okay, that's going to be the answer. And then 5. How many unpaired electrons are there in Fe3 plus ion? Similar to chromium, you have to first find out atomic number for iron 3 plus iron, just for the iron, and iron is Fe number 26. Okay, 26. Iron is 26. So prior to iron, noble gas is argon. And then after argon, it's going to fill the 4s2. So it would be 4s2, and then you fill up your d electrons up to iron. D3d1 2 3 4 5 6. So it's going to be 3d6. 4s2 3d6 is what iron going to be. So in iron 3 plus, so we are doing number 5. How it's asking how many unpaired electrons are there in iron 3 plus iron. So first we have to find out what is the electron configuration for iron 3 plus. So this is for iron. 3 plus would be 3 electrons lost. First these 2 will be gone, and then it's going to go 1 from the 6. So then it would be argon and 3d5 when 1 electron lost. So 3d5 meaning in your 5 electrons, 5 d orbitals, 1 2 3 4 5. Okay, so there are 5 electrons. So 1 2 3 4 5. So these are all unpaired electrons. So how many unpaired electrons are there in Fe3 plus ion then? That's going to be 5 unpaired electrons. Okay, number 6. A certain transition element has the stable oxidation states of +2, +3, +4, +6 and +5 and 6. In which state will the element be most likely to form an ionic bond with chlorine? Normally we talk about this in the lecture also, lecture videos. Ionic compounds are being formed with the lower oxidation states. Covalent bonds are being formed with the higher oxidation states. Like with +6, it would form covalent bonding, but with +2, it would form ionic bonding. Okay, so most likely to form ionic bond is with +2 ions. Which of the following is considered bidentate ligand? Bidentate means there are 2 places in the same ligand that can coordinate with the central atom. So thiocyanate does have 2 atoms, but it's not going to be bidentate. It's monodentate. One atom can join at a time, either S or N. NO2 nitrite is also not bidentate. It has only, it can participate either through nitrogen or through oxygen, but not by both. Nitrogen, NO2 minus. It can participate either this oxygen or through this nitrogen, one at a time, but not at the same time. Okay, so it's not NO2, not cyanide either, but C2O4 2 minus. How does it look like? C2. So I explain this oxalate ion. This is how it look. So this is a bidentate ligand because these 2 oxygens that I'm drawing lone pairs right now, they can participate bonding to the central atom at the same time. So it is a oxalate. C2O4 2 minus is the bidentate ligand. Number 8, what is the coordination number of cobalt in the complex ion? Given here. Okay. Coordination number is the how many ligands are connected to the central atom. But some could be bidentate ligands. So then there are two sites that it can coordinate. Now here the central atom is cobalt. En stand for ethylene diamine. Ethylene diamine look like this. CH2, CH2, and it has two NH2 groups like this. So through the nitrogen, it can coordinate to the central cobalt atom. So this is also a bidentate ligand, ethylene diamine. Okay, this is En, a bidentate ligand. And there is only one ethylene diamine. So nitrogen, CH2, 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 hydrogen. And then there are 4 chlorides. 1, 2, 3, 4. So this is the structure of the complex ion. The coordination number is how many ligands are attached to cobalt. So if you count, so this is 1, 2, 3, 4, 5, 6. So that tells us that the coordination number is 6. Okay. And number 9, the oxidation and coordination numbers of the cobalt in the compound. Again, the coordination number is going to be how many coordination sites this central atom has. So we have cobalt and there are 5 ammonia and 1 chlorine. So 5 plus 1, the coordination number is 6. And then we also need to find out the oxidation number. Coordination number 6. Let's find the oxidation number. So this is a complex cation, right? So we have a square bracket over here. And then you have Cl2. Each chloride is -1 since there are 2 chlorides. So the negatives are 2, -2. Anion. So if the chlorides outside the square bracket is -2, so then your positive ion is going to be +2. So cobalt complex ion charge is +2. So to find out what is the coordination number for cobalt, you take the charge +2 and you subtract the ligands attached to the cobalt. So there are 5 ammonia ligands plus 1 chloride, right? Ammonia doesn't have a charge, so it's 0, and chloride has a charge -1. Chloride is a -1 ligand. So +2 minus -1, make it +1. So cobalt +2 plus 1 is +3. So the oxidation number is +3 and coordination number is +6. Number 10, in the compound potassium simple cation, and then you have cobalt with oxalates and water. So C2O4 is oxalate and there are 2 of those. We want to find out the oxidation number and the coordination number. So let's see how this complex looks like. So cobalt in the center and then the C2O4. Remember I told you C2O4 is oxygen. This is carbon. Carbonyl group. So there are 2 of those. Oxygen, oxygen, carbon, carbon, like this. And there are 2 water. This is the structure of the complex. So what is the coordination number? How many coordinating atoms are there. So this is 1, 2, 3, 4, 5, 6. So the coordination number is 6. Okay, and the oxidation number. You see here we have a simple cation, potassium. Potassium is +1 charge. So then the complex anion charge should be -1, the whole thing. Now we need to find out what is the oxidation number for cobalt. So to find that, you take the charge of the complex anion, -1, and you subtract the ligands attached to the cobalt, which is 2C2O4. So C2O4 means it has -2 charge, and there are 2 of those. So -2 times 2 is -4, plus the water. Water is a neutral ligand, so it is 0. So negative will make its +4, -1, so the cobalt is +3. Charge of the cobalt is +3, which is the oxidation number +3 and coordination number 6. Number 11. Give the systematic name for this complex. So we have a complex cation. So let's see what is the oxidation number for cobalt. Okay, so here how to find out. So there are 2 chlorides, meaning charge of the anion is -2. So the charge of the cation, complex cation, should be +2. Okay, so to find out the charge of the copper, +2, you subtract charge of the ammonia. Ammonia is a neutral ligand, so the charge of the ammonia is 0. So copper therefore +2. So then we have to write the name as, there are 4 amine groups. So 4 means tetraamine. So it's going to be tetraamine copper 2 chloride. There are 4 amines, so tetraamine. Copper we found it's 2. Copper 2 chloride. Okay, so tetraamine copper 2 chloride. The next one has a simple cation and complex anion. Compound potassium and the complex. Okay, so we want to find out the systematic name. Since it's a simple cation, we just have to read the cation as potassium. Let's see how to figure out this guy over here. Since potassium charge is +1, oxidation number, there are 3. So positive is going to be +3. So this whole complex charge going to be -3. To find the ion, charge of the ion, -3 minus the charge or the charge of the ligands attached to the ion, Fe. So cyanide is -1. So -1 times 6, -6. Right? So -3 plus 6 make it +6. So ion is +3 oxidation state. So the name going to be potassium. And then this is an anion. So anion would end as 8. So there are 6 cyano group. So it would be hexacyano. Hexacyano. And since it's iron is ferrous, that would go as ferrate. Ferrate, and then the oxidation number 3. Potassium hexacyanoferrate 3. Yes, that's going to be the answer. And number 13. Write the formula for pentamine cobalt 3 chloride. pentaamine. So there are going to be 5 amine groups and cobalt. So it's going to be a complex cation, cobalt with 5 ammonia groups with a chlorine, and it says chlorocobalt, pentamine chloro, pentamine coco, pentaamine chloro cobalt 3 chloride, Cl. Now we need to see how many chlorides are going to be there. To do that, we need to find out the charge of this complex cation. It says the cobalt is +3. So cobalt +3 over here, from here. And then ammonia is a neutral ligand, it's 0. And there is one chloride group in the complex cation. So the chloride charge is -1. So +3 - 1 +2. So the charge of the complex cation is +2. So then the charge of the anion also need to be -2. To make that -2, so then you need 2 chloride groups. So the formula is going to be this one with 2 chlorides at the end. Okay. The next one, number 14. Which of the following ligands could participate in linkage isomerism? Linkage means that there are in the same isomer there are 2 places that it can participate in coordination at a time. So ethylene diamine, it cannot participate as linkage isomerism, it's just a bidentate ligand. Ammonia also has 1, and NO2 is this. In fact, this one can participate in linkage isomerism. One time it can coordinate through nitrogen, and then the other time it can coordinate through oxygen, but not at the same time. So NO2 can participate in linkage isomerism. Next one, which of the following could exist as isomers? Isomers could be cis and trans isomers that I explained in the lecture videos. So for this one here, there are 3 ammonia and 3 bromide in platinum. So this is your platinum. So you put bromine, then you put another bromine here, another bromine here, and then ammonia, ammonia, ammonia. 3 and 3. So even if you try to put it, so this is octahedron geometry, you try to put it in different ways, it would somehow look alike because it's 3 and 3. So it cannot exist as isomers. You can play with this complex and see. And then you have 3 ammonia and 1 chlorine. You cannot do anything with that either. And then for this one you have 4 water and 2 chlorides. Okay, so if you take cobalt and you put 1 chlorine here, 1 chlorine here, and water, 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 and water. So here the 2 chlorides are opposite with each other. And you can draw another one like this. Cobalt here, you can have chlorine right there, and then chlorine, water, and like this. Now, are these two the same? No, right? Because this chlorine and this chlorine opposite, whereas this chloride and this chloride are close together. So they can participate in cis-trans isomerism. So that can exist as isomers. And this also cannot because you have platinum in the center. And ethylene diamine is this guy, NH2, NH2, and then you have CH2, CH2 here, and then the chlorine, chlorine. So this is a ring bidentate. So you try to do it in another way, it would end up being the same thing. So only C can participate in cis-trans isomerism. Okay. All right then. Talk to you later.